Hey, Year 12s. How's it going, guys? Okay, guys, right. Let's get on with this, shall we? Metallic bonding in one lesson. Just get it boxed off. Then you have one piece of homework, which is one assessed piece of homework. It's lit, and I don't need to freak out about it. Metallic bonding in one lesson. Okay. Anyway, so you'll have one piece of homework, which I'll send you guys out on the Google Classroom. You can do it, and I'll mark it. So it's just to show you the link between theory and questions from the papers. That's it. But anyway, let's crack on, shall we? So, 3 learning objectives. We're going to box off metallic in one lesson. Okie dokie. Got my little fan set on my laptop. We had a full meltdown earlier. It was an absolute nightmare. Freaked out. Can I ask everyone just to post a quick message on the chat for me, just to make sure that you guys are there? There's Aisha. Brilliant. Okay, so recall GCSE. Okay, so the great thing about metallic is it can be done in one lesson. It's a very basic topic because essentially we don't really teach it to you properly. We teach you kind of like the base foundations of metallic bonding, but we don't go into that first year degree at any stage. It's relatively straightforward. So what did you get at GCSE? So let's do the GCSE recap. So you got very few things at GCSE. Number 1, you got the fact that you have pure metals and you got a diagram. You got pure metals, and this is what your diagram looked like. I'm just going to do, let's choose a metal. Let's do iron, yeah? And you got a picture that looked like this. Yeah, and we said that they were well organized in layers, yeah? Pure metals. They are organized in layers. They are organized in layers, and those layers can slide. Layers can slide. And this is your explanation. This here is your explanation to the question of explain malleability. Explain malleability. Yeah, malleability. There we go. And then you got alloys. And then we got alloys. And the example being that you had to learn at GCSE was steel. Now, steel was actually then subdivided. It was subdivided into low carbon steel, and high carbon steel. So the diagram is actually, you're not showing a screen. Oh no, darn it. Ugh. Everyone's just looking at my forehead. Nightmare. Screen. Yes, I get it. All right. Share screen. All right. Sorry. Okay. So, there are the learning objectives. So we had our diagram at GCSE. Is that better, guys? When will he realize? Thanks, Louis. Thanks for that. You're so lovely. Yeah. Thanks, guys. Anyway, are you happy now? Someone post on the chat, please. Forgot to share screen. Haven't done that in a while. Are you there? Can you see it? Yes, sir. Fabulous. Yep, so at GCSE, so the first learning objective, recall GCSE metallic bonding. Next, understand metallic bond strength. Number 3, be able to compare metals. So the first thing you got at GCSE was pure metals, this simple diagram, and you talked about there being organized in layers, and those layers can slide, and that explains malleability. Then we picked up alloys, and we actually picked up 2 specific alloys at low carbon and high carbon steel, and the picture was the same. You did iron, and then you added in a smaller carbon. And what you realize from this diagram, yeah, if you actually do it nice and slowly, you can actually make it do exactly what you want it to do as a teacher, which is, it was doing so well then. Trying too hard now. I've stuffed that up. Come on. Better. That'll do. Iron, carbon. Yeah. And what we talk about here is in this diagram, so you have alloys, and alloys are stronger than pure metals. Alloys are stronger. And the question is why? And what we say is that you lose the layers become disrupted. That's what we want to say. The layers become disrupted because due to having atoms of different sizes. You guys are all remembering this. Different sizes. Therefore, layers can't slide as easily. Layers can't slide as easily. There we go, GCSE. Now, just to bring in the high carbon and low carbon steel. So, as a result, when you subdivide steel into these two types, what it's important to do is to compare all three. So, if we just say iron versus steel, yeah, iron versus steel, yeah, and what we realize is if we had a piece of metal that was pure iron. Now, just to let you know that pure iron does have a name. It tends to be called wrought iron. I know, go figure. Wrought iron. Or wrought, I think, actually probably comes from the word raw of some variety. Or wrought being the fact that it's very bendy, very malleable. And wrought iron is used for things like gates. Now, wrought iron is often described as soft, which is rather entertaining, isn't it? Because it's not if someone hit you with a piece of wrought iron, it's not like it's going to be like, oh, it's okay, it's as soft as a pillow. But it's soft compared to steel. If we were to bend this, yeah, it would take quite a lot of force, but it could be done. Yeah, it could be done. Yeah, we can bend this. Yeah. It's not easy, but it's malleable. Now what you get, the next piece, if we were to compare a similar piece, we now have low carbon steel. Yeah, so this is now low carbon steel. Now this is much stronger. And you're talking, by the way, you're talking about 10 times stronger. You know, this is a big increase in strength. Now, there are lots of YouTube videos where they actually show this and they can actually demonstrate it using hydraulic presses. If we were in school and we had a DT department, I'd be taking you down to bash stuff with hammers. It's a lot of fun, but we don't, sadly, which is rather upsetting. But low carbon steel, it can still be bent. It can still be bent, but it's much, much tougher to bend. That's not right. It's a lot more challenging to bend at this point. Yeah, much more difficult. I did a much better job of the last one. I did that, and then, yeah, it's not really worked out, that, has it? Why has that not worked out? I don't know. So, it's not worse, just the other one looks okay. And then, no, I just don't think it works out, does it? And then, I don't know. I'm trying to bend it. It's not working out very well in my diagram. Don't know why. The last one was okay. I'm just going to clone it. Clone. Edit, copy. So you let me do that. Edit, copy. No! Oh my God. Oh my God. You stupid laptop. It's just kicked off on me as well. Delete. So what I want to do, draw, select. Oh. There you go. Copy. Paste. So you can still bend this one, but the force you need is about 10 times more. You know, it's much, much harder to bend low carbon steel. But then what happens is you get to high carbon steel. Now, high carbon steel at this point is no longer bendable. It's lost the malleability entirely. This is commonly referred to cast iron. It's a common name. And you cannot bend. No bendy. Yeah. So you might have come across this. So just to show you this as a picture, You may have come across this in IKEA, because if you go to spoon cutlery smashed metal, I wonder if there's going to be a picture of this, images. So if you buy stuff from IKEA, you find that the spoons are the cutlery is incredibly hard. That's actually low carbon steel. I know that stuff in IKEA. By the way, I actually have a collection of different forks and spoons from IKEA because they're different examples of the different grades of steel. But you can get, what you realize is things like, a knife blade. A knife blade is high carbon steel. What you don't want to be doing is halfway through cutting something and it bend. So it's high carbon steel, so it becomes very, 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 very hard. Let's see if I do it better. Let's do a smashed metal. That'll work. That's bending, so that's not high carbon steel. What we want to see is when something cracks, when something actually shatters. I will be able to find one. I will. Let's go smashed metal train wheel. Train wheels have high carbon steel, and when after so long, they actually tend to shatter rather than. Oh, come on! Just show me an example of. Let's type in high carbon steel shatter. Let's try that. High carbon steel shatter. Okay. So it's still not being very helpful, is it? It's rubbish. The internet's garbage. Come on. Samurai swords, high carbon steel. Samurai swords are actually that's actually much more complicated because actually they layer it. They have low carbon steel on the inside, and then they have high carbon steel on the very outside. So the skin of the blade is high carbon so that it remains sharp. But then the inside provides it with some form of flexibility. I can't find any pictures of shattered steel. Oh, finally, but it's an ancient one. It's not what I'm looking for. I just want shattered steel. Come on, I don't have time for this. Shattered steel. Oh, it's a computer game? Are you for real? Stupid thing. Have you guys ever broken a sharp knife? No. Oh, I can't find it. It's garbage. Forget it. Moving on. So it doesn't bend. If you try and bend that, what will happen is it will simply crack and shatter. Yeah, it'll actually just crack in half. Yeah, like that. It loses the property of bendy, of malleability. Yeah, and it's called cast iron commonly. So, and this is all to do with the amount of carbon. The more carbon you add, the less those layers can slide, and eventually they stop being able to slide altogether. So we actually add other metals and things like carbon into a metal in order to increase its strength. Okay, it also changes the melting points, by the way, and plus it also changes their corrosion resistance. So if you're interested, stainless steel, just to add in a third one. Yeah, stainless steel. Stainless steel. Instead of adding, by the way, it's still a steel. So we now have a mixture of iron, carbon, and chromium. And chromium prevents it from rusting. Sharing properties there, corrosion resistance. It's nice. Okay, so next thing, metallic bond strength. Right, can we now do metallic bonding? Metallic bonds. Still GCSE. Yeah, we now then, at GCSE in year 11, we picked up an evolution. We picked up this picture. You have a giant lattice of cations. A giant lattice of cations surrounded by a sea of delocalized electrons. And those electrons are free to flow through the structure. Yeah, this is why they can conduct electricity. Okay, I shouldn't have done that one. That was a bit stupid. This is why they can conduct electricity. So this picture all of a sudden changes things entirely. So we are now using this to explain. So now, if we're going to do explaining, a couple of things. Explain, number one, high melting point. High Melting point. Okay. Susan Boyle sings Nelly the Elephant. Susan Boyle sings Nelly the Elephant. Structure. Right. This is a bit more complicated now because this one is where things differ. Yeah, we now have to do a much better description of the structure of a metal. So we say a giant lattice. Yes, lattice means repeating pattern. A giant lattice of cations surrounded by a sea of delocalized electrons. Delocalized electrons. Right. Bonds. The electrostatic attraction. There is the electrostatic attraction between cation lattice and delocalized electrons. Strength. This attraction is very strong. This is what makes metals strong. This attraction is very strong. It's giant. Number. Millions of attractions. Energy. Lots of energy. Needed to break all. I'm going to put metallic bonds. Yeah. To break all attractions. Yeah. Now, sometimes you tend to see, Edexcel don't tend to do this, but sometimes that you'll find textbooks on the internet referring to this, the bond section here. This is not Edexcel, by the way, so just beware. The internet's a great resource, but it does have some garbage chemistry. Sometimes referred to as metallic bonds. Yeah, but that's not allowed in Edexcel at all. You have to say it's the electrostatic attraction between the cation lattice and the delocalized electrons. Yeah, this attraction is very strong, millions of attractions, lots of energy needed to break. So we now get this, and that's still GCSE. Yeah, that is a GCSE question. Okay, so what we also need to do is explain why they conduct electricity. So number 2, why do they conduct? Can I just point out, by the way, that they conduct in all states. Metals conduct as solids. Why do they conduct? Solid, liquid, and gas, amazingly. Yeah, metals always conduct. Always. And that's an important thing now. They never, ever not conduct electricity. So why do they conduct? Metals contain delocalized electrons. Delocalized electrons. These electrons, let's do these electrons. These electrons are free to move and flow through the structure. 3 marks at A level. Yeah, flow through the structure. Done. Right. So that now covers pretty much all the GCSE questions. I do just want to mention a couple of people. It's nice to mention aluminium at this point. Aluminium is one of those metals that you just have to know about. It's an important metal. Aluminium. So just some facts about aluminium that I want to give you. Number 1, very lightweight. Hence why it's used in planes and spacecraft. Very lightweight. Number 2, very corrosion resistant. It doesn't rust. Corrosion resistant. Yeah, this is good because you means you can have it out in the rain and it just doesn't matter. It's not going to rust. Yeah. Number 3, it's very abundant. Lots of it. I'm going to say readily available resource. Yeah. Lots of it. Lots of it. Number 4, extracted by electrolysis. By electrolysis. You can watch my GCSE video for that one. But aluminium comes up a lot. Yeah. Oh, there's also a fantastic conductor of electricity. Very, very good. A very good conductor of electricity. Now we're going to go into explaining that conductor of electricity. I like it. Okay. So now we actually step into the A-level bit. So the A-level bit is understanding metallic bond strength. Okay. So A-level. It's not a huge leap, really. So we understand that it is the force of attraction between the giant lattice of cations. The giant lattice of cations, they're all slightly different sizes. Hilarious. Yeah, the giant lattice, it's just that one that's bugging me. The giant lattice of cations and the sea of delocalized electrons. So we have got a negative C, and a positive lattice. Yeah, and a positive lattice. Okay, so the great thing is this is like a bit of an evolution from ionic, really, because the same factors apply. So if we're calling this here the electrostatic attraction between these things here, notice I'm not going between the ions, but just between them and the C. Yeah, they're not actually touching those wiggly lines. Yeah, because it's the attraction between the electrons and the cation. Yeah, so what factors would affect this strength? So metallic bond strength. Number 1, let's do factors. Number 1, charge on ion. Charge on ion. So if we have sodium compared to magnesium, immediately we know that sodium is going to be an Na+1 ion and the magnesium is going to be an Mg2+. The 2+ is going to increase the strength. Number 2, the number, I'll write it properly, the number of electrons in the delocalized C. In the delocalized C. So the more electrons, the stronger the attraction. Stronger attraction. Stronger electrostatic attraction. Cool. And last but not least is the size of the ions. Yeah. So it's nice to recall the smaller the ion, the stronger the bond, the higher charge density. Yeah, which means a stronger electrostatic attraction. Yeah, the smaller the ion, the stronger the attraction. Right, now that we've got all that boxed off, we can now compare every metal on the table because that's all we need. Yeah, so let's do some comparisons. So let's go back to my beautiful, gorgeous periodic table. Love my table. Look how beautiful it is. Let's choose 3 people in a row, just for fun. Let's go for these guys. Oh, it's not a highlighter. Is that a highlighter? Oh, that's rubbish. Oh, that's irritating. It's no actual highlighter. Let's go for him, and him. So sodium, magnesium, and aluminium. Right, let's have a look at what they look like. So we're now going to compare. Let's compare sodium metal, magnesium metal, and aluminium metal. Okay, so let's now draw each one of their diagrams out. We know that sodium started life, with one electron in its outer shell, it is going to lose that electron to the C. And I am going to form this picture. Na+, Na+, just going to draw 4 in the lattice this time. Yeah, there we go, there's sodium. Now, each one of the sodium atoms has lost one electron to complete its outer shell. So how many electrons will be in the C for this image? The answer is 4. Each ion has lost one electron to the C. So I'm going to have 4 electrons in this delocalized C. Yeah. Let's go to now magnesium. So magnesium is in the same period. Yeah, so it had the same at the beginning, like sodium, it had 3 shells. But it was smaller because it had 11 protons. Same shielding. These guys here have the same shielding, but magnesium has more protons. But now the magnesium is going to lose 2 electrons to the C. So it's going to become smaller Mg2 plus ion. Let's draw 4 of them. Mg2 plus, Mg2 plus, and Mg2 plus. How many electrons in the C? The answer is 8. 2 from each person. 2 from each of these atoms is going to lose it into the C. They're going to become 2 pluses. Yeah, they can flow through the structure. Yeah, there we go. So all of a sudden, what would we predict in terms of melting point? So on the chat, please, which one of those 2 is going to have the higher melting point? Let's go to aluminium. Aluminium, same period, same 3 shells, but it's smaller than magnesium because it's got the same shield, actually no, similar shielding, because it's now got an outermost electron in the 3p. So it's actually got similar shielding now. It's a tricky change in words, that. Sodium and magnesium have the same shielding, but magnesium to aluminium have similar shielding. The extra shielding from the 3s underneath. But it has 3 electrons in its outer shell. Yeah, these are all going to hop off. Yeah, aluminium has an extra proton, so it's going to become tiny. Here's aluminium, Al3 plus, Al3 plus. I think I've gone a bit OTT on that, if I'm honest. There we go. That's okay. So they get smaller. Not only are they becoming more charged, but they're also becoming, they're also becoming smaller. Louis, aluminium, magnesium, sodium. Louis, highest to lowest is correct. Well done, Louis. Yeah, we've now got how many electrons in the C? We went from 4 in sodium, each one losing 1, to magnesium of 8, each one losing 2, and then aluminium, who's now got 12 electrons in the delocalized C. 12 electrons. And hence, why is it such a good conductor of electricity? Because there are boatloads of free delocalized electrons to flow through the structure. Yeah? I'm not going to bother doing the wiggly lines. It's just going to look like a mess. So here, we've got +1 cation and 1 electron per cation. Magnesium, Mg2 plus cation, higher charged than sodium. 2 electrons per cation in C. Increase electrostatic attraction, stronger, higher melting point. Aluminium, Al3 plus, higher charge cation, also smaller, 3 electrons per cation. Stronger electrostatic attraction. So we can now start making predictions here, which is really cool. So let's do the next one. So we've just gone across a period. Yeah, we've just gone cross a period. Now we need to go down a group. Let's go down a group then. All right. Yeah, now we're going to go down a group. Go away. I don't know why it's not. There we go. Let's go down a group. Zoom in. Down a group. So we're going to look at, let's do group 1. Why not? So we've got lithium. Oh, I've got to be careful here. So we've got lithium +1. And then we have sodium +1. And then we have potassium +1. We can now make predictions. Who's going to have the highest melting point and why? Pause the video. Have a go. Yeah? Question. Highest MPT? Question mark? Explain? Question mark? Right. So the highest is going to be lithium. Lithium metal is the highest. The question is why? Well, we can't compare their cation charge. We could say all have +1 cations. All have one electron per cation in the C. So hang on, so what's different? The answer is the size. Lithium cation is smaller, higher charge density, so stronger electrostatic attraction. Static attraction. Okay, cool. Lithium smallest. All have the same number of electrons and same charge. Well done, Louis. Great job. Electrons in the delocalized. Yep, absolutely right, Louis. You're doing great. So lithium has a melting point of about 205 or something. No, 198. Got 198 in my head from somewhere. 198 MPT. Sodium is 98 degrees MPT. Potassium is like, I don't know, 75. I'm making that one up. Don't know what potassium is actually. Gonna have to Google that now. Oof. Lithium melting point 180. Damn, so close. Just remember to double sodium. That's kind of what I did, to be fair. So 180. There we go. Let's see if I get sodiums right. Am I going to get sodiums right? 98. Come on, sodium. Come on, sodium. Boom, 98. Yeah, nailed it. Potassium's a complete guess. I have no idea. Potassium, but I can predict it's lower than sodium, 63.5. There we go. I like it. So, nice predictions. Makes total sense. Lowest with potassium, largest cation size, weaker electrostatic attraction, and lower charge density. We're done. Right, so we can now recall GCSE and its properties, talk about and understand the bond strength in terms of charge on cation, number of electrons in the delocalized C, and the strength and the size of the ion. Now we've been comparing metals. I'm going to add something else. We talked about alloys. Let's mention some alloys. So A-level alloys. I don't know why it's not moving. That was weird, isn't it? Go figure. So, A-level alloys. Oh. A-level alloys. So, the most famous alloy asked at A-level is the one used on pretty much every spacecraft. Yeah? And the thing is, you see, when you're building a spacecraft, yeah, Elon Musk and his Raptor engines. There we go. When you're building a spacecraft, you want it to be as light as possible, but strong as well, but also it must be able to be flexible, because if it's not, when it would take off, it would just shatter like glass. You need this to be strong, you need it to be light, and you need it to be flexible. So we're looking for an alloy with a low something. We don't want to go for a high something, because high something becomes brittle. We want a low something. And what they do is you'd like to use aluminium. Everyone loves aluminium. But the problem with aluminium is it's just too soft. Yeah, aluminium is just not strong enough. Pure aluminium, what a great choice. It's corrosion resistant. It's not going to rust. Aluminium. We love aluminium. Images. There we go. But the problem is it's just not strong enough. Yeah, if you hit aluminium with a hammer, you're going to cause some serious damage. Just look at your laptops as a great example. You know, it's good because, you know, you drop it on the floor and it doesn't shatter. Yeah, but you'll certainly dent it and cause quite heavy damage. So they needed to make it stronger. Now, the thing is, what they need to do is they need to take the aluminium and they need to add in another metal. And what metal would you choose? Well, you need to make this as light as possible. They add lithium, which is actually a very interesting example. So they add lithium. They add lithium to make an aluminium lithium alloy. Now, this one is quite a famous one because it's quite an interesting mix here, because you've got lots of aluminium 3+s, but you're actually introducing a very small, and even smaller than aluminium, I believe. Oh, that would be nice to know, wouldn't it? Periodic table of ions. Periodic table of ions. Let's look at the sizes. Table of ions. Come on. Give me what I want. There. Hello. Look at that. Ooh, lithium is larger. Look at that. Isn't that fascinating? I'm not entirely sure if I trust it, but sure. So, blimey, even though lithium has aluminium has an additional shell, the 3+ ion has made it smaller. So actually, the picture now actually reverses. We've got lithium 1+, and we've got the tiny aluminium 3+s, Al3+. So what this means is you disrupt the layers. Now you actually remove. Now the great thing is you don't need much of it. You need only a little bit, and the size is doing exactly what we want it to do. Disrupt the layers. The layers can no longer slide as easily, increases its strength. But not only that, but the bonus is the fact that the aluminium has an atomic mass of 27, and the lithium has an atomic mass of 7. Or in 6.9 actually for you at A level. 6.9 aluminium, I think it's 27.0, yeah. So you actually are dropping the mass of your alloy hugely. So this one is a classic disrupt layers. Disrupt layers cannot slide as easily. Yeah, it also makes it lighter. Good for a spaceship. Now, the thing is though, if you want to make something much, 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 much stronger, I mean, you want to make something crazy strong. What you want to do is you want to be starting to sub in. You want to start subbing in. So I'm going to do another famous alloy now. So we can do magnesium. So they started using magnesium in sports cars. So sports car magnesium chassis. Let's see if I can find a picture of chassis. Let's have a look. Right. So they started using magnesium for MG engine cradle. Yeah. They started using it for sports cars to build really lightweight frames. High strength, but low weight. That's, of course, what sports cars are all about. So there's a problem, though. So hang on a minute. The next famous alloy is, we talked about spacecrafts and the lithium aluminium alloy. This one now is for sports cars. It's for your sports cars. I can't draw a sports car that quick. Definitely not. Definitely can't draw a sports car. Oh, it's not going well. Yeah, sports cars. I don't know quite why I did that. Should have just done that and then added on like a windscreen or something. There we go. It's better. There we go. So this is sports car. Sports car. I don't like the fact that was rubbish. I don't like that. I feel like I want to fix it and do a better job of the picture, but whatever. Sports car parts. Things like chassis. Now, they want to use something lightweight. Magnesium is a great choice. Magnesium has an atomic mass of 24.3, I believe. There we go. 24.3. It's even lighter than aluminium. You can't use anything lower because that is the toughest metal we can get at that weight. Yeah. So they wanted to use magnesium, but the problem is there was an issue with magnesium. Number one, it burns really badly when it catches fire, but trying to set fire to that kind of quantity of magnesium is borderline impossible. You have to melt it first. It's a nightmare. But the problem was it just wasn't strong enough. So what they needed to do is, how do we make this piece of magnesium, how do we make this bar of magnesium stronger? We've got a lattice of 2+, 2 electrons in the C per ion, etc. What they do is they now add to it aluminium. They now add a small amount of aluminium. Now, why is this beneficial? Because number one, here's the pure magnesium, Mg2+, Mg2+, organized layers, 2 electrons in the C per cation, plus 2 cation. Yeah, let's draw that in. I'm going to need 8 of these guys. 8. I think that's 8. Yep. So now what we get is we now add in the Mg2+, we now have the tiny aluminium 3+. Not only does this add charge, not only does this add higher charge cations to the lattice, but it also dumps more electrons into the C. So MgAl alloy is stronger. They're going to ask you to tell them why. Explain. And you would say, added a cation of higher charge, Al3+. Yeah. Also, more electrons now in the C. Instead of having, so in this picture, we had this guy here. This guy donated him and him to the C. And this guy here, I should call it, this guy here donated him and him to the C. Well, we've replaced them now. So this guy is now, let's count the electrons in. So I need from this magnesium here, this one is going to give me him and him. So this aluminium is going to give me him, and him. This aluminium is going to give me another 3. Let's do them in purple as well. Yeah, him, and him. And then the last one, this magnesium, again, gives me 2 more blues. So I now have an extra 2 electrons in the delocalized C. So more electrons in the delocalized C. And just as a kicker, as a third point, aluminium 3+ is smaller than Mg2+, higher charge density, therefore stronger electrostatic attraction. So, stronger electrostat attraction. Loads of really cool electrostatic attraction. Done, that'll do. So that actually brings us to the end of A-level metallic bonding. That's all you guys need to be able to do. Compare down a group and across a period, make predictions, talk about properties in terms of low and high carbon steel, be able to draw your basic pictures still from GCSE, and that brings us to the end of metallic bonding in one lesson. It's been nice. We're done. Let's bring that to a swift conclusion. That was nice. I'll set you guys a homework on the classroom. There we go, I'm back. I'll set you guys a homework on the classroom, guys, for you to have a go at. And I'll see you next lesson for giant covalence. See you soon, guys.